all my friend and Dr. Susanna. Today I will present our group project 3D Terrestrial laser scanning for aircraft analysis. Before I start our presentation, I will introduce our group member. This is Shokalab, Eng Weza, Nur Naziha, Nur Ilya Izzati, Yang Jinyi, and me, Nur Sharabda. Okay. The laser scanning or TLS is a higher addressable instrument that finds significant application in a variety of fields. Its success to managing difficult tasks and quite obtain millions of 3D point cloud. Let's explore how the flexible of TLS influence our work process and see small detail in 3 dimensions. First, one of the more notable aspects of 3D laser scanning is the way it's able to produce accurate geometric information. In the aviation sector, where data collection is needed for performing precise aerodynamic analysis and modified design for improved performance and efficiency, this provision become important. Second, experience of paradigm shift in aviation analysis with the revolution impact of 3D terrestrial laser scanning. This technology transforms the landscape of data acquisition and processing, provide a game-changing approach for the aviation industry. With the high-precision geometric capture of aircraft parts, 3D TLS generate density point cloud. This cloud play an important role in structure inspection and maintenance process, ensure a comprehensive understanding of aircraft integrity and facilitates informed decision making.
Method study to this project, utilizing three-dimensional data is important for improved aerodynamic efficiency and safety in aircraft. Three-dimensional data visualization and analysis provide valuable insight into the connection between structure dynamic, control, and aerodynamic. This enhances overall understanding and contribute to optimize aircraft performance. The use of three-dimensional data also raises safety standards in aviation. Then, surface of motion photogrammetry is a cutting-edge methodology for aircraft analysis. It involves capturing overlapping images from various angles. Then this enables precise 3D model reconstruction with exceptional detail. Surface of motion photogrammetry assists in examining complex aircraft structure. It is particularly effective in capturing intricate features. The methodology contributes to a comprehensive understanding of aircraft geometry and its applicability enhance research, development, and maintenance practice in aviation.
Hi, my name is Shokalab, and now I'll be presenting the aim and objective of this project. The aim of this project is to let students to get familiarized with 3D terrestrial laser scanning equipment and software for practical use. In order to achieve the aim, 3 objectives are being set. First, to implement the application of 3D terrestrial laser scanning (TLS) for generating 3D models for aircraft analysis. Second, to generate the 3D models of aircraft using structure for motion SFM technology. Third, to evaluate the accuracy of the generated 3D model aircraft using measurement comparison method. The study area of this project is the 2 aircraft, which is the blue one and the white one, located at the front of Aerolab, Faculty of Mechanical Engineering, UTM. The equipments that will be used in this project are Topcon GRS 2000M, tripod, prism, measuring tape, hammer, roofing nails, warning tape, and a handphone used to capture image for SFM. There will be 3 software used in this project, which is Manicollage, used to read the point cloud file and do pre-processing, Archisoft Metashape Professional to perform SFM, and CloudCompare to generate 3D model. Now is planning and schedule. In the first week, the study area is being identified. After that, set recognition is being done, and this project was proposed to Dr. Susanna. After the proposed project being accepted, we started our data collection on week 2, and 2 days were used to collect data due to the rainy day. At week 3, data pre-processing is started. After that, week 4, we were busy with data processing, and the result and analysis of this project were done in week 5 and 6. At the same time, Report preparation and video presentation preparation was started at week 6, and the presentation will be held on 18 January 2024. Now, I'll continue with field methodology. First, we need to set up 3 stations, which is the backside station, labeled as B in the figure, an occupied station for TLS, labeled as TLS, and a foresight station, labeled as F. After setup, since we use coordinate instead of bearing distance here, therefore we need to set an assumed coordinate at TLS. Then we'll do backside scan, which labeled as step 1. Since we doesn't have the coordinate of backside station, a target scan to backside station were needed. Then we'll perform backside scan again and check the different height. If the difference is below 10 mm, then it's acceptable. Next, we'll perform target scan to foresight station, which is labeled as step 2, to obtain the coordinate for the foresight station for further use. If more station is visible from the occupied station, we can perform target scan as well, but if not visible, we are required to move the TRS to another station which is visible to each other. Lastly, we will start scan to obtain point cloud data of the surrounding. As mentioned earlier, if the foresight station is not visible, we need to move the TRS to another station that is visible to each other. In this case, the foresight station is visible to the TRS, and target scan can be done. While the backside station, any station can be used as long as the coordinate has been obtained using target scan and are visible between the backside station and occupied station. While for the methodology for equipment, first is set up TRS. The level of the X and Y should be within 10 seconds. Then open a new file for this station and select setup and select occupied/backside. Then key in the occupied name, instrument height, and backside name as shown in the diagram. When key in the occupied name, key in as well the assumed coordinate or true coordinate for the occupied station. Next is to perform backside scan. Select backside scan and then the camera will be open. Face the camera to the prism and select the icon to widen the screen. Remember to choose the correct target type, which is prism. Then apply the zoom in and zoom out function to aid in targeting the prism. Remember as well to check the height of the prism, which is labeled with red rectangle box, is correct or not. After that, select check and see the different height. Different height is -1403. It's because no coordinate is recorded in the TLS for the backside station. Therefore, we need to select OK and back to the home page. Then select target scan. Aim the prism again and start scan. After that, back to occupied/backside and perform again backside scan and select check to see the result. If the result is within allowable, which is 10 mm, then can proceed to the next step. If not, repeat from the first step. After the backside scan, now we will perform foresight scan using target scan to obtain the coordinate used for the TLS to occupy later. Make sure the name and the height of the foresight station is correct, and then select start to perform target scan. Repeat this step if more visible foresight station occurs. Lastly, we'll select start scan to collect the surrounding count point. Remember to check the result after finish the scan in order to identify whether more station needed to cover the missed scan part.
Open the news workspace, select and add scan project, select GLS 2000 PRJ file and click OK. Let's all the file load before proceeding on, and all TLS station already shown as figure above, so right click project file and select process scan and image, refer post scan and select start. Wait until the processing is done and apply it to all observed stations. The whole point cloud data that collected, double check the point cloud is acceptable or not. So now we need to do occupation and backside registration. Select report and determine whether the Z value is acceptable. If not, we need to do some adjustment. Now we select strat map to see the overall point cloud collected by using the TLS from a top view. And this is the overall point cloud after the registration. Now we will do some data cleaning by using the polygon. Choose the specific region of the point cloud that require to study. Select delete to clean the unwanted point cloud. Proceed with removing the unwanted point cloud. And lastly, the Jet A and Jet B point cloud from the TLS shown in figure above. And after the data cleaning, this point cloud already to be used for next processing. So now for the Agisoft MetaShape Professional, number 1, select all the photos that already taken by using the smartphone. Select the align photo. As you can see, type point already generated after align photos. Double check the point cloud from the smartphone is acceptable or not. Now let us proceed with the build dense cloud. Dense cloud done generated. And now we need to do some data cleaning to remove the unwanted point cloud. After the data cleaning, now we can export this point cloud which collected by using the smartphone to LAS file for the next processing later. For the cloud compare, number 1, select the file which are from Agisoft MetaShape Professional and also the file from the Magnet Collage software. And as you can see, data already import. Select the file and select the align to cloud by picking Jet B represent TLS and Jet B represent for SFM. Select the data from Jet B SFM as a target of alignment. Determine the body part of the jet that is easy to identify to serve an alignment marker for Jet B, which represent for SFM. Establish marker for Jet B. Determine the body part of Jet A that is easily identified to serve the alignment for Jet B by using the TLS. Establish marker for Jet B. Select align. Select the file that already aligned, then choose merge multiple cloud. As you can see, I already done the alignment. So now I will show how to generate the 3D mesh model with the following step. And now as you can see, the 3D model of Jet B is nearly formed. And now we want to smooth the surface of this 3D model. And finally, 3D model which combined with TLS and also SFM is formed.
Come the sun, come the rain, and the leaves falling. I'll wait, even if the seasons change. Anxiety runs through my veins. I'll escape from all the strains.
The results show a 3D model of an aircraft captured using TLS combined with SFM techniques. These two combinations allow for the creation of highly detailed and accurate 3D aircraft models as shown in this video. This is Jet A. As for the measurement, they show very slight differences between the two methods, measurement tape and TLS. This leads to the conclusion that the TLS method provides precise measurement due to its use of laser technology for scanning and measurement. This is the result of Jet B. Both results highlight the geometry and surfaces of the aircraft with different shading indicating depth and surface variation. This technology is a part of the broader field of digital twinning, where physical objects are accurately represented in the digital world. From both results, we have achieved the three objectives of this project.
Now I will talk about the limitation of terrestrial laser scanning, TLS. One of the limitations is line of sight. TLS cannot capture data from surfaces that are not visible to the scanner. This means that surfaces that are blocked by the scanner's line of sight cannot be scanned effectively. Let's say the scanner is unable to reach certain areas behind obstacles. This limitation limits the completeness of the data we can obtain. Second is complexity. Processing TLS data can be complex and may require specialized knowledge. Not everyone has the ability to interpret the data and extract meaningful insights. So, this complexity may pose a barrier to widespread use of TLS technology. Third is coverage. TLS has limitations in the area it can effectively cover. Although TLS is very effective at capturing detailed information within the line of sight, it has difficulty covering large areas effectively. Last of the limitation of TLS is precision. The precision of TLS data can be affected by random range errors, which are differences in distance measurements. So these errors can affect the precision of scan data, especially when extracting small details. Now we proceed to limitation of structure from motion, SFM. One of the limitations of SFM is image quality. The accuracy and reliability of the reconstruction depend on the quality of the input image. Poor image quality, characterized by low resolution, blur, or distortion, can result in inaccurate 3D models. Another aspect to be aware of is the possibility of generated objects or inaccuracy in the model. In some cases, the reconstructed model may have distortions, such as waviness or incorrect features. So these differences may be due to the variety of factors, including the camera calibration errors or challenges in the feature matching process. Last but not least is reflective surfaces. SFM has difficulty accurately reconstructing scenes involving highly reflective surfaces such as glass or mirrors. The reflective nature of these surfaces can make image matching difficult. Because of the algorithms may have difficulty identifying corresponding features. Next. So these are the recommendations for obtaining a good result in this survey. First of the recommendations is multiple angles. Capture data from various angles to ensure a complete model and to mitigate the line of sight limitation. Second is complementary use. Combine TLS and SFM to leverage both technology strengths and improve model completeness and accuracy. Third is redundancy in image content. Ensure a high amount of redundancy in image content to improve the robustness of the SFM model. The fourth one is avoid reflective surfaces. When capturing images for SFM, avoid reflective surfaces to prevent issue with image matching. Last of our recommendation is regular inspections. For infrastructure and maintenance, perform regular inspections using TLS and SFM to monitor changes over time. That's all from us. Thank you for the listening.